In this video, I would like to look at complex exponential function and see what it's doing visually and understand its property much better. So let's take a look. Okay, so complex exponential function. So we could look at this function. It's e to the x plus iy. And we could also break it up further to e to the x. So that's the real exponential function that we know and love. And we have e to the iy. And e to the iy, we could use Euler's formula. So cosine of y plus I sine of y. And here we go. So if you want to look at the e to the z as like a real functions, here's the real part and here's the imaginary part of that. At the end of last video, I asked you to check this function to see if it satisfies Cauchy-Riemann equations, and it does. So it is another example of complex analytic function. Let's look at some of the properties of this function. Okay, if you want to look at the modulus, or how big this output is, it's really controlled by the real part. So e to the x is the real part, or it's where the real part of the input goes, and the imaginary part of the input actually doesn't contribute to the size because e to the iy always has modulus 1. So really, the modulus is controlled by the real part. The imaginary part controls the argument. So if you just want to look at the argument of the output, you can look at the argument of e to the x times e to the ay. E to the x just stretches this complex number. So really, the argument is controlled by the imaginary part. And we know the argument is the angle y. Okay. One thing to note is that there's actually many different arguments for any one output. So I said y here, but really I could add any multiple of 2 pi or subtract any multiple of 2 pi, and it'll be the same angle. Okay. I guess this is a similar point. So if we have e to the z plus 2 pi I, if I'm adding 2 pi I to the imaginary part of the input, that shifts the argument by 2 pi. But on a unit circle, if you add 2 pi angle, you get the same angle. So you get back what you would have plugged in without adding 2 pi I to the input. This means that the exponential function is 2 pi I periodic. So it's periodic if you add 2 pi I in the imaginary direction. Okay. And this is something that we shouldn't assume, but thank God it's true, is that if you add 2 complex numbers in the input, you could break up the real and imaginary parts. And because both the real and imaginary part obeys the exponential rule, where you can break it and then with the same base, what we get is that you would get the same thing if you apply exponential function to both of the inputs separately and multiply the result together. So adding before in the input has the same effect as multiplying in the output. Just a note here, this seems like an obvious fact about exponents that we already know, but we already knew it for the real number case. So it is something new that we're learning, that it still holds for complex exponent as well. Let's see, 1 over e to the z is same thing as e to the negative z, because if you multiply e to the z to e to the negative z, because of the previous property, we could add the exponents, get 0 here, e to the 0 is equal to 1. That means that e to the negative z is the multiplicative inverse of e to the z. E to the z is an entire function because this thing is defined for all x and y, any real x and y just fine. Derivative exists and it's complex analytic everywhere. Okay. What is the derivative? Well, hopefully the derivative of exponential function is itself, as it is for as it was for calculus 1, and that is true. So if we take this function, both of these, take the derivative with respect to x, that gives us the derivative, and it's exactly the same function. So I've written that here. Derivative of e to the z with respect to complex variable z is e to the z. Chain rule holds. So derivative of e to the az is going to be a times e to the az for any complex a. This holds because of the chain rule. The complex conjugate is respected. So if you take the complex conjugate of the input, that gives you the complex conjugate of the output. And that's really because if you take the negative of y, cosine of negative y is same thing as cosine of y. So the real part is not affected. And then if you take the negative y here, since sine is an odd function, you can pull the negative outside of the sine function, and then you'll get the negative of the output. Okay. All right. So let's see. E to the z is equal to 1 if and only if x is equal to 0. And that has to be true because the modulus of 1 is equal to 1. And the only way to get the modulus of 1 is if e to the x is equal to 1. And that only happens when x is equal to 0. And of course, the argument has to also match. So the argument has to be 0 or any 2 pi multiple, 2 pi I multiple of added or subtracted. Okay. This translates to if two complex complex exponential function are equal to each other, if and only if the real parts are the same and the imaginary parts could possibly be off by a multiple of 2 pi I. Okay. So this is very important. I want you to understand what the function is doing visually, like geometrically. So I want you to follow along with me. So the exponential function. So sometimes, because when we write exponents in the superscript, things get very tiny and hard to read. Sometimes people write exp of z to mean exactly the same thing, except now that z is not in the superscript. So if there's a complicated expression in there, you know how to read it. So when I write exp mean the same thing as e to the z function. All right, we know that this function looks like e to the x times cosine of y plus I sine of y. Okay, so let's try to understand what this function is doing. Let's see horizontal lines and see how that gets mapped. So if I fix some imaginary part, why not? And x could be any number. So I'm looking at horizontal lines that look like this. Okay. What does this do in the output? Well, if we fix y naught, that means that we're fixing a particular angle in the output. And then as far as the real part goes, so the real part is ranging from negative infinity to positive infinity as it goes from left to right. And e to the x will be anywhere from 0 to infinity, right? It doesn't quite hit 0, but as x gets closer and closer to negative infinity, it gets closer and closer to modulus 0. And as x gets larger, it will blow up in modulus. So the angle is fixed, and you get modulus anywhere from 0 to infinity. So you might get something like this. And this is a particular angle, why not? But with different angles, it's going to look like rays coming out from 0. It doesn't actually hit 0, but all horizontal lines will look like rays coming out of the origin. I hope that made sense. Let's see what happens with vertical lines. So now we're fixing a particular x naught, right? So here, the modulus is fixed, but argument is allowed to vary. So lines that look like this in the input. So all of these vertical lines will correspond to particular modulus. So it's fixed in a circle. Circles. And as y vary, it goes around and around in circle. Okay, in fact, it'll wrap around many, many times, right? Every time you go up by 2 pi I, it'll come back to the same spot. So there's lots of circles being wrapped around many, many times. I hope that makes sense. If you think you understand this picture so far, I'd like you to pause the video and now reason for yourself. What would a vertical strip where the real part is fixed between -1 and 1 and y is allowed to vary, what does this set look like in the output? And I want you to also try to analyze what would horizontal strip look like. Here, let's restrict the y between -1 and 1, and x is allowed to vary. So pause the video, try to see if you can sketch it for yourself. And I'll show you the picture now. So I'm assuming you gave an honest shot. And here's what the graph might look like. Okay, so x is between -1 and 1. That means in the output, these are circles of radius 1 over e and e. and y is allowed to vary. So it'll wrap around this entire circle. So everything inside of this donut, I'm going to shade in. So it'll look like that. As far as the image of t under the exponential function, the angle is restricted between radian 1 and -1. And the modulus could vary anywhere from 0 up to infinity. So we're going to get like a cone like this. And that's what the horizontal strip T would look like. Okay, this would be 2 radians. Okay. How did you do? This kind of visual thinking is very important for the rest of the class. So I'd like you to practice this. If you didn't do so well, try to see if you can sketch what the square box or rectangle might look like under the exponential function. I will see you in the next video.